All right, 2.8. So in 2.8, we're going to talk about applied optimization, which is kind of interesting from a calculus perspective. Really, we're not going to learn any new calculus techniques that we didn't learn in the previous section when we learned about optimization. So in a sense, applied optimization is nothing new. However, from the student's perspective, when you see applied optimization problems, they feel very different than optimization problems. So what I'm going to focus on in this section is a lot of examples to kind of work out all the different types of problems you might see and try to kind of argue how they're really the same thing that we learned in a previous section after you do a little bit of algebra. We'll encounter two different types of problems, kind of the two variable type and the one variable type. So in these first few videos, I'll focus on the two variable type. And really, the fact that it's the two variable problem is what makes it so different than what we did in the previous section. Because all the optimization we did before only involved one variable, right? Think about a graph like this. Our variable is the letter x. The output to our function we represent with the y. And we have some sort of graph right here. And we're trying to optimize, meaning find a local minimum or a local maximum. So maybe we're searching for this point right here by taking a derivative and setting it equal to 0. And then recognizing that because the graph is concave up, that point must represent a local minimum using our second derivative test. Anyways, here's a classic example for what you'll see with applied optimization. Say you want to build a fence because you want to fence in a rectangular plot of land. So kind of picture something that kind of sort of looks like this. Here's the land you're going to fence in, and here's your fence. But there's a problem. You only have 120 feet of fencing in order to build this thing. So I could make this, 10 feet, 10 feet, 50 feet, 50 feet, right? That would be 120. But I don't want to just pick the length and the width arbitrarily. What I want to do is fence the largest area possible. And so maybe we can kind of translate that idea. When it says we want to fence the largest area possible, what that means is we want to optimize or maximize the area. And because it says that we're fencing a rectangular plot of land, figuring out area is pretty easy. Area is just length times width, right? So maybe I call this the length right here, and this the width. Area as a function of length and width is just equal to length times width. So when the length is 50 and the width is 10, the area as a function of length and width would be 50 times 10, in other words, 500. And so already this should feel very different than what we did up here. Again, the big difference being over here we only have one variable, the letter x. Down here we have two variables, the L and the W. And we don't know how to optimize, or at least we didn't learn how to optimize when we have two different variables. How do you do this with this function? Well, the short answer is you don't. What you do instead is you change this two variable function into a one variable function so that you can do what we learned in the previous section. How do you do that? Well, there's a constraint. Remember, we only have 120 total feet of fencing. So I can't make this 100 and this 200 and this 100 and this 200. We'd run out of fence. Because we only have 120 feet of fencing, the perimeter of our fence can't be more than 120 feet. And rather than make this an inequality, I'm going to make it an equality, because if we're trying to fence the largest area possible, it makes sense that we're going to use all 120 feet, right? If you come up with some configuration that only uses, 110 feet, I can get more area by just extending either the length or the width. And maybe more important than any of this is kind of the big picture view that what you're seeing here is very common. You have a function that you're trying to maximize, and that function involves two different variables. However, there's more information given in the problem. And maybe the problem has nothing to do with fencing. I mean, who knows what the problem's about? But there's something that it says we're trying to maximize or minimize, optimize, and then some other piece of information. And that other piece of information serves as a constraint which will allow you to make the function that you're trying to optimize one variable. How do you do it? Well, what you try to do is you try to write an equation that relates together the variables that are being used in your two variable equation. So remember, because our plot is rectangular, area is length times width. However, I can write the perimeter in terms of length and width also, because the perimeter is just the distance around the outside of this rectangle. So it's width plus length plus width plus length. In other words, twice the length plus twice the width is the perimeter, and the perimeter has to be 120, whatever my unit is, feet I think it was in this case. We've got a function that we're trying to maximize that involves two variables, but we got a constraint that relates together those two variables. So all we got to do is solve this constraint for one of the variables. It doesn't really matter which one we solve for, although when we get really good at these, the variable that we choose down here to solve for can make our work easier later on. But ignore that for now. Just pick either of your two letters, it doesn't matter which one, maybe L, and solve for that. 2L is equal to 120 minus 2W, and therefore L is equal to 60 minus W. I can write the length in terms of the width, so then I can come up here to my function, and instead of writing area as a function of length and width, I can write area as a function of just width, because instead of writing L times W, I'll write 60 minus W, which is what L is equal to, times W. Start out with a two-variable function. Recognize you can't optimize, with our techniques, a two-variable function. However, note that there's a constraint that you can use to write one of the variables in terms of the other variable. Substitute it into your original function to make it a one-variable function, and then you're good. This is something we learned how to optimize in the previous section. I mean, maybe you didn't write it with these letters. Maybe you wrote f of x equals 60 minus x times x, and I asked you to find critical values and then classify those critical values as local minimums, local maximums, or neither. We're just going to redo that exact same thing, except kind of with some different letters. So in the last section, our first step was to find the derivative of this function. So let's find the derivative of this function, a prime of w. Can you find a prime of w? Absolutely. Either you can use the product rule here, or you could take this w and distribute it through and rewrite your function as 60w minus w squared if you didn't want to use the product rule, and take the derivative of that. The derivative of 60w is just 60, and the derivative of w squared is 2 times w. The derivative of area with respect to the width of my fence is 60 minus 2w. Remember, to find our critical values, we got to take the first derivative and set it equal to 0. So we have to solve when is 60 minus 2w equal to 0. Well, that's pretty easy to solve. Add 2w to both sides, and then divide by 2, and we get w is equal to 30. This is our only critical value, so this must be our answer. Okay, I'm being a little bit lazy there. This is our answer, but really you don't know that that's the right answer at this point. What you should do is make sure that that point represents a local maximum and not a local minimum. How do you do that? You classify this critical value. The easiest way to classify this critical value is to look at the second derivative, a double prime of w. The second derivative is just the derivative of the derivative, and the derivative of 60 minus 2w is just negative 2. So I want to evaluate my second derivative at my critical value when w equals 30. So I copy this equation right here and I change all the w's into 30s. Well, there are no w's on this side of the equation. I have a constant function, so the second derivative is just equal to negative 2. What that tells me is that my function is concave down at this point. So you're kind of picturing a graph that looks like this. At a point where the graph is concave down is a local maximum. And I guess really we shouldn't stop here, because this problem technically has endpoints also, right? We can't make the width of our fence any less than 0. Nor can we make the width of our fence any more than 60, because if we did, our length would end up being negative. And maybe you recall from the previous section that when you have endpoints, things get kind of messy, and really what you have to do is kind of plug those into your original function to make sure that our local maximum is an absolute or global maximum. Well, it turns out they are, because if the width is 0, then your area is going to be 0, because 0 times anything is 0, and if the width is 60, well, then your length is equal to 0. So again, your area is equal to 0. So we're definitely not going to get optimal solutions when w equals 0 or w equals 60. Technically, when I get this answer, I should check to make sure that my function is concave down and it represents a local maximum if I'm looking for a maximum. And then I should compare that local maximum with any endpoints to make sure that the local maximum is a global maximum. However, as your teacher, I can tell you that these problems are going to be written in such a way that the answer that you find, the critical value, is going to be the optimal point that you're looking for. I'm not going to write any trick problems where the endpoints ended up being better. I'm not going to write any trick problems where that critical value was actually a local minimum and not a local maximum. It's good if you know that you should do all this stuff, and it's good if you learned all this stuff in the previous section, but in this section, you can skip that. At this stage, when you find your critical value, if there's just one critical value, you can assume that that's the optimal point, that w equals 30 is what you're looking for. One more comment that I want to make. This was a 2-variable problem that we switched into a 1-variable problem and then solved. We figured out that the width equals 30, but did we really answer the question? Often what you'll have to do in these problems is reuse the constraint to solve for the other variable, right? If you go back up here and look at what we were looking for, the question asked, what should the dimensions be? We figured out that the width should be 30, but that's not the dimensions. To know the dimensions, we need to know the length and the width. Fortunately, our constraint up here will always be solved for the other variable, because the way we got rid of the L's in this two variable equation was substitution. And in order to do substitution, we had to solve for the variable that we were substituting out. What I'm saying is we can reuse this form of our constraint, that L is equal to 60 minus W, and the fact that W is equal to 30, to figure out that L is equal to 60 minus 30, in other words, 30. Oh, the length and the width are both 30. Yeah, that makes perfect sense. If you're trying to fence the most area possible, your rectangle is going to end up being a square. Right? Maybe you can kind of see that if you took a little bit off the length and made this 29, well, then you can make this a little bit longer. This would be 31. You'd be losing all this area and you'd be gaining all this area, but you're losing a little bit more than you gained, because this is maybe 1 by 29, whereas this is 1 by 30. Anyways, the point that I wanted to make is just make sure you finish the problem, right? If they ask for the dimensions, you're not done when you figure out width. You have to figure out the length and the width. And on that note, make sure you're reading what they're asking for really carefully. In this problem, they asked for the dimensions, but a very similar problem could have given us all the same information and asked how much area can we fence if we have 120 feet of fencing. If that's the case, when you get up here and get W equals 30, you're not done, because it wants to know what the area is. Fortunately, you have area written in terms of that variable W. You have to, because that's how you figured out W, by taking the derivative of this function. So if the question asked how much area could you fence, all you'd have to do is say, well, area as a function of W is 60 minus W times W. And if we evaluate this area function when W is equal to 30, our critical value, we get that area is 60 minus 30 times 30. We get that the area is 30 times 30. In other words, 900, I guess, square feet is what our unit would be here. Oh yeah, I could have figured that out up here, because once I knew both the length and the width, I could get the area by just multiplying these two numbers together. Yeah, that's kind of what you did down here. You just didn't need to know length and width because you were able to rewrite the area function in terms of just W. Before I end this video, I want to do one more version of this same problem to make sure that this is really sinking in. It's this problem. It says, what if one side of the plot didn't need to be fenced? And maybe I should write it a little bit carefully, but I know what I'm talking about, and I knew that I would be talking you through this example. It's saying that now our rectangular plot of land kind of looks like this pink rectangle, where the width is this distance and the length is this distance. So the area of our rectangle as a function of length and width is still the length times the width. And we're assuming that we still have 120 feet of fencing to use. So that's still our constraint. However, now we don't have to fence one of the sides because, I don't know, there's like a river here or something. So that 120 will be used for this length, and this length. It'll be twice the width plus 1 times the length if I'm calling this the width and this the length. We have a slightly different constraint, which will lead to slightly different optimal dimensions. So just like we saw before, we want to pick one of our variables here. It doesn't matter which one we pick. Maybe I'll pick L again and solve for that variable. See, if I subtract 2W from both sides of the equation, I get L as 120 minus 2W. Now that I've written L in terms of W, I can substitute that in here. Instead of L times W, I'll say it's 120 minus 2W times W. I can change the L into 120 minus 2W because my constraint allowed me to solve for L in terms of W. If I want to optimize the area, I have to find critical values. To find critical values, I have to take the derivative. I could take the derivative of this thing the way it's written right now, or I could distribute the W so I don't have to use the product rule. Maybe this time I'll use the product rule just to kind of show off all the calculus that I know. I got the derivative of 120 minus 2W times W. The derivative of the first thing is -2. Leave the second thing alone. Add to that the derivative of the second thing, which is just 1. Leave the first thing alone, 120 minus 2W. I got -2W plus 120 minus 2W. I got 120 minus 4W as my derivative. The reason I found the derivative is because I'm looking for critical values. The way I find critical values is I take my first derivative and I set it equal to 0. So I got 120 minus 4W equals 0. Add 4W to both sides. Divide both sides by 4, and I get that W is again equal to 30. Now that I know W, I can figure out L, because L from up here in my constraint is just 120 minus 2 times W, And since W is 30, it's 120 minus 60, which is equal to 60. If I didn't need to fence one side of my plot, the way I would capture the largest area possible is I would make the width equal to 30 and the length equal to 60. Kind of interesting maybe that we don't change the width at all. We just take the 60 feet that we're going to be used for length on both sides of my rectangle and use that all on one side. Really at this point, I should take this critical value where W equals 30 and make sure that it represents a local maximum, because I'm trying to find the maximal area that I could fence. In order to make sure it represents a local maximum, I should look at the second derivative, a double prime of W, which is easy enough to figure out because I have a prime of W written right here. The derivative of 120 minus 4W is just negative 4. If I evaluate that second derivative at my critical value when W equals 30, I get negative 4 because there's no W's over on this side of the equation to change into 30s. What this tells me is that my function a of W is concave down when W equals 30. So because I have a critical value at W equals 30, that means W equals 30 represents a local maximum. I really should do all this, but you'll note that I wrote optional up here because for your purposes, if you skip this, it's totally fine. But I would like you to understand what's going on kind of behind the scenes. Another comment is we could figure out how much area we're fencing when W equals 30 because we have the area as a function of W written up here. All we got to do is copy this equation, changing all the W's into 30s. We'd get 120 minus 2 times 30 times 30. 120 minus 60 is 60, and 60 times 30 gives me 1800. Oh yeah, I knew that from this picture up here. This 30 times this 60 gives me that same 1800, a more visual way of figuring out, a more algebraic way of figuring it out. Finally, I guess I should look at endpoints, which in this case would be when W equals 0 and W equals 60. I can't have the width be less than 0. And because the length is 120 minus 2W, I can't have the width be more than 60. Otherwise, the length is less than 0. So really, I should look at these endpoints and evaluate A of 0 and A of 60. But what you see is in both cases, we get 0. Because if either the length or the width is equal to 0, then the area is going to be equal to 0. I'm certainly not going to be able to fence more area than I was at my critical value. This didn't really ask a question, but if it said what would be the optimal dimensions if one side didn't need to be fenced because there was a river there, you'd say the optimal dimensions would be to build a rectangular fence where the width is 30 and the length is 60. And if it said, what's the most area that you could fence if you didn't have to fence one side of your rectangle because there's a river there, you'd say the maximal area would be 1,800 square feet. What we'll see in future videos is we can do kind of the same thing if we're talking about different situations. This doesn't only work, I'm sure this doesn't surprise you, if we're talking about rectangular fences. And it can feel really different if we have different types of problems, and that's why we'll do a few examples so that when you see things, they're more familiar to you.